This is the Atomic Energy Commission's Nevada Proving Grounds, where atomic tests were conducted in the spring of 1952. One of the major military projects in this series of tests was the study of the effect of atomic bombs on parked aircraft. When the project was assigned to the Structures Branch of Aircraft Laboratory, comparatively little information was available concerning the condition of complete airplanes following an atomic attack. One B-17 and one F-47, which were exposed during Operation Buster Jangle, furnished only limited data on this subject. The new project was designed to determine the effects on a number of aircraft structural types and to relate these effects to variables of overpressure, thermal energy, orientation with respect to ground zero, and angle of incidence of the blast. Although the 28 aircraft employed were primarily obsolescent types, most of them were flown to Yucca Lake and then towed 8 miles to the test area for... This illustration depicts the primary ranges at which the aircraft were deployed for the first detonation at Yucca Flat, which was shot number 2 of the series. To provide a variety of input and response data, the aircraft were deployed at 2,200, 4,000, 8,000, and 10,500 feet. 3 of the ranges were prepared with black top and oil in order to stabilize the dust. Wall, pit, and G-type revetments were included in the test to obtain data on the protection provided by these devices. This is a typical array of aircraft at the various stations in relation to each other and to ground zero. Ranges were based upon expected damage levels of severe, moderate, and light for shot number 3. These sketches show the aircraft as they were positioned for this shot. Only fighter-type aircraft were exposed at the 2,200-foot range for shots 2 and 3 because the expected overpressures would be destructive to bombers. These fighters were exposed in a variety of attitudes relative to ground zero for the purpose of studying the different types and levels of damage inflicted on aircraft oriented nose in, side in, and tail in. At the 4,000-foot range, one F-47 was stationed behind a wall revetment, one in the open, and one in a pit-type revetment. All 3 aircraft were oriented the same so that a comparison of the effects on each could be made and the effectiveness of the revetments determined. At the 8,000-foot range, 2 fighters were placed in a G-type revetment and the other aircraft in the open. It was expected that the unprotected fighters at this range would suffer moderate to light damage, the bombers severe to moderate. At the 10,500-foot range, it was anticipated that the bombers would receive moderate to light damage and the fighters little or none. Flying over the atomic test site prior to shot 2, the 3 stations A, B, and C can be seen during the preparatory phase. Here at Station A, range 2,200 feet, a large blacktop area installed for Operation Buster Jangle was reused for Project 3.1. This is Station B, range 8,000 feet, where most of the instrumented aircraft were exposed. The orange tower provided an elevated camera position. Note the F-47s in the G-type revetment. Prior to Shot 2, Station C at 10,500 feet served as operational headquarters. The semi-trailers grouped in the foreground were outfitted as an operations office, machine shop, instrumentation, and photographic laboratories. At this headquarters, on-the-site planning and supervision of the test installation was accomplished. Placement of the aircraft constituted only a small part of the preparatory work. 44 motion picture cameras were used in 24 pedestals to record during shot reaction of the aircraft. Operation of these cameras had to be remotely started by timing signals with appropriate time delay devices so that the camera run would cover the desired period. Instrumentation of certain aircraft included wing and tail bending moments, center of gravity acceleration, reflected pressures, and heat input into the cockpit per unit area, and skin temperature, all versus time. Calibration of instrumentation systems was performed at the site. Each station was also instrumented for blast overpressure, heat input per unit area, and angle of incidence of the high-velocity air mass. Automatic recording instrumentation equipment was buried in pits and remotely started by timing signals. Power for operation of the cameras and oscillographs was supplied by remote source and by batteries. All timing signal and power wiring were buried for protection against damage by workers, vehicles, and the detonations. 60 tons of lead bricks were used to shield the cameras and the oscillographs against nuclear radiation. In addition to the study of aircraft structure, items of equipment and materials were exposed by laboratories. Modern propellers were installed on some of the airplanes to study the effects during the blast. Engines, electrical and hydraulic systems, radio equipment, and instruments were inspected before and after each shot. For shot number 1, a camera installation utilizing a 55-gallon drum as a photographic target was made to determine suitable exposure conditions and the effects of pre-shock dust and smoke from soil stabilizing oil. Shot number 2 was a 1 1/4 kiloton device detonated on 15 April 1952 at an altitude of 1,109 feet above the ground. Overpressures of interest were expected only at the 2,200-foot range. 3 F-47s and 1 F-90 at that station received approximately 6 calories per square centimeter total thermal energy and 5 pounds per square inch overpressure. Wherever possible, the following motion pictures show the aircraft before, during, and after the blast. This is the nose-in F-47 at the 2,200-foot range as it was photographed from the camera pedestal. Pre-shock dust and smoke provided an effective screen, which was persistent enough to obscure portions of the photographic results during the blast phase. This aircraft suffered slight damage, consisting of cracks in the canopy and buckled skin immediately aft of the cowl flaps. An estimated 8 man-hours would be required to repair the airplane. The F-90 was also oriented nose-in and sustained slight damage. The stainless steel skin panels in the aft fuselage section were badly buckled. Access doors were blown off, and the right fire door was warped and buckled. The canopy received 4 cracks along the front and top. Complete repair of this airplane was estimated to require 160 man-hours. This left side-in F-47 was severely damaged. Major damage occurred to the left side of the fuselage from the engine accessory section to the empennage. The stringers and frames in this region were permanently deformed. The surface of the vertical stabilizer and the rudder buckled, and the lower hinge attachment bracket pulled loose. The canopy was shattered. It was estimated that complete repair would require 1,150 man-hours. The control surfaces of the tail-in F-47 were severely affected. Landing flaps and ailerons were damaged beyond repair. The elevators were scorched and buckled. Approximately 157 man-hours would be required to completely repair this airplane. Station B, here photographed from the 25-foot tower, received only 0.8 pounds per square inch over pressure and 1/2 calorie per square centimeter total thermal energy. Even at these low input values, a slight formation of pre-shock dust occurred. No damage resulted at this range. However, several views of the responsive aircraft will be shown to indicate the severity of the blast loading at an overpressure of 0.8 pounds per square inch. This F-47 in the G revetment was oriented side-in. There was comparatively little response of the aircraft because of the small input forces. In this pedestal view of the nose-in F-47, which was one of the instrumented airplanes, passage of the shock wave can be seen. This F-47 was oriented tail-in. The low overpressures at stations B and C during Shot 2 made it possible to have a complete operational run of the cameras and oscillographs in preparation for the main effort which was to be made on Shot 3. This view of the side-in B-17 clearly shows the skin wrinkles due to thermal radiation and later buckles caused by the differential pressures acting on the inside and outside surfaces during passage of the shock front. After each detonation, the engines of the aircraft, most of which contain fuel, were started and checked for proper operation, provided inspection indicated that the fuel system was intact. Before Shot 3, the tail-in and side-in F-47s, damaged by Shot 2, were repositioned to nose-in orientation at 1,000 feet and 1,384 feet from ground zero. Undamaged F-47s from Station C were used as replacements at the 2,200-foot station, and an additional F-47 was placed at a 45-degree nose-in orientation. The 3 F-47s at the 4,000-foot station were changed from nose-in to right side-in. The B-45 at the 8,000-foot station was changed from right side-in to nose-in. On the morning of 22 April 1952, a 31-kiloton bomb was detonated at an altitude of 3,450 feet above the ground and produced overpressures at the test aircraft stations varying from 10.7 to 2.4 pounds per square inch. The corresponding thermal energy varied from 61 to 5.5 calories per square centimeter. The pedestal photography at the 2,200-foot range was obscured by the dense pre-shock dust and smoke. This F-47 at 1,384 feet and the one at 1,000 feet were damaged beyond economical repair. The entire airframes were burned and buckled, and the internal structure severely damaged. All thin, unsupported skin directly exposed to the thermal radiation vanished. All of the F-47s at 2,200 feet were damaged beyond economical repair by the overpressure of approximately 8.5 pounds per square inch and thermal energy of 48 calories per square centimeter. However, the types of damage varied considerably with orientation, except that all the aircraft here were scorched and had skin burned out. This tail-in F-47 suffered complete loss of flaps and one aileron, with pieces blown as far as 50 feet. Wings and fuselage were severely buckled and damaged internally. Much of the top skin was burned out. Numerous failures occurred to miscellaneous parts, such as the canopy and the tail gear. The 45-degree nose-in F-47 rotated over 100 degrees clockwise about the vertical axis. This movement tore off the tail wheel. The right horizontal stabilizer and elevator completely failed in bending and torsion. Many stringers failed in the wings and fuselage. Flaps and ailerons buckled but were not blown off. As a result of the blast, the right side-in F-47 was pivoted about 90 degrees. The whole aircraft was badly buckled and damaged internally, as was the nose-in F-47, except the damage to the latter was more symmetrically distributed. Both aircraft suffered widespread miscellaneous damage. The F-90 fared considerably better than the F-47, as indicated by a repair estimate of 250 man-hours, whereas the F-47 was damaged beyond economical repair. A portion of the upper wing of the F-90 was buckled aft of the rear spar, but most of the damage was limited to the access doors and the aileron assemblies. The stainless steel tail cone skin buckled deeply. This is Station B, range 8,000 feet, photographed from the 25-foot tower during Shot 3. The greatest number and variety of aircraft were exposed at this station, including 4 instrumented for wing and tail bending stresses, reflected pressures, thermal radiation intensity in the cockpit, skin temperatures, and center of gravity acceleration, all versus time. The positive and negative phases of air mass movement are evident in the motion of the dense pre-shock smoke and dust, which rose to the height of the tower. This is the tail-in F-47 at Station B. All the aircraft at this station were subjected to an overpressure of 3.5 pounds per square inch and a thermal radiation energy of 10.3 calories per square centimeter. As was typical of tail-in fighters for overpressures at this range, the flaps and ailerons failed in bending. Fuselage damage consisted mainly of skin canning and a buckled radio door. The elevator torque tube connector and the fin spar flange failed. Elevator travel was displaced from neutral. It was estimated that complete repair would require 222 man-hours. This F-47 was oriented nose-in. The wing and empennage were not damaged. The fuselage skin was buckled around the radio access door and the belly cowls. The tail wheel moved and castered, causing failure of the internal fairing around the tail wheel strut on the left-hand side. The canopy was cracked on both sides. 24 man-hours was the repair estimate. This instrumented F-86 at 8,000 feet was oriented nose-in. Minor positive pressure damage was sustained by the aileron upper surfaces. There was a slight buckling of the fuselage just forward of the ammunition doors. Portions of the headrest and the rubber coating on the nose were burned. The leading edge of the wing and the empennage were slightly discolored. It was estimated that 333 man-hours would be required to completely repair the airplane. This nose-in B-17 was one of the 4 instrumented aircraft at the 8,000-foot range. For test purposes, several propellers representing different structural types were installed on this airplane. Although fighter aircraft at this range suffered only light to moderate damage depending upon orientation, the B-17 type bomber aircraft here were all damaged beyond economical repair. Although the least damaged of the lot, this nose-in airplane suffered many crushed ribs in the wings and tail, crushed rings and bent stringers in the fuselage. In addition, the bomb bay doors were crushed in about 10 inches, and nearly all of the windows were broken. In this close-up of the side-in B-17 at 8,000 feet, note the formation of wrinkles in the vertical skin. As previously stated, the thermal radiation intensity at this station was 10.3 calories per square centimeter. The blast overpressure loading of approximately 3.5 pounds per square inch incident upon the vertical tail in this side-in configuration resulted in complete failure of the fuselage between the trailing edge of the wing and the empennage. One of the major problems which could not be considered in these tests was the separate effects of overpressure and thermal radiation and their interrelation. For example, it could not be determined at this time how much of the apparent blast damage resulted from the weakening of the structures by high temperatures. This is the tail-in B-17 at 8,000 feet as photographed from a pedestal during shot number 3. As was the case with the nose-in and the side-in B-17s, this airplane was damaged beyond economical repair. Extensive damage suffered by the entire airplane included the almost complete destruction of the wing structure aft of the rear spar. The fuselage was a total loss due to the bending and crushing of frames and stringers, as well as a general distortion of the skin by pressure loads. The B-45 was oriented nose-in at 8,000 feet. The more rugged construction of this modern bomber, compared to that of the B-17, is readily apparent from the amount of damage sustained. The general wing structure showed no damage. There was some buckling of the fairing on the nose of the engine nacelles and the tail gunner's cone, and between the dorsal fin and the vertical stabilizer. The bomb bay doors were blown in. Several small doors, such as the main landing gear doors and the life raft compartment, were buckled. It was estimated that the damage, which was mostly superficial, could be completely repaired in 300 man-hours. At Station C, the 10,500-foot range, this side-in F-47 was one of 2 F-47s placed at this station, along with the nose-in B-29 and 3 B-17s oriented nose, side, and tail-in during shot number 3. These aircraft were subjected to an overpressure of 2.4 pounds per square inch and a thermal radiation intensity of 6.4 calories per square centimeter. This airplane received only minor damage, which would require about 45 man-hours for repair. The tail-in F-47 at Station C was only slightly damaged. The ailerons were slightly buckled, and the canopy was cracked on both sides. The repair estimate was 8 man-hours. All of the B-17s oriented at 10,500 feet suffered heavily at the relatively low overpressure of 2.4 pounds per square inch. This side-in B-17 was the hardest hit. Internal damage to the ribs of the wings was not as severe as the internal damage to the fuselage, which had a torsion and side-bending failure at the wing root trailing edge. In spite of the severe damage, it was estimated this airplane could be repaired in 5,500 man-hours. Repair estimates for the tail-in and the nose-in B-17s were 3,700 and 3,500 man-hours respectively. Damage to the B-29 consisted mainly of skin buckles, except for the bomb bay doors, which were destroyed. It was estimated that the B-29 would require 800 man-hours for repair. For shot number 4, the aircraft were repositioned to provide data on overpressure and orientation parameters necessary to supplement information secured during shots 2 and 3. Evaluations of the results of shot 3 indicated that the test points of major interest extended from 2,200 to 8,000 feet, which covered an overpressure range from 9.5 to 1.8 pounds per square inch. 18 aircraft were exposed in this region. Since shot number 4 was the last one in which Project 3.1 would participate, most of the aircraft were moved to ranges where they would be subjected to more critical loads. Extremely damaging overpressures were expected as far out as the 2,200-foot station. The fighters closest to ground zero, although severely damaged by shot 3, were left in position at the 1,000 and 1,384-foot stations. One F-47, which had sustained serious damage at the 2,000-foot station during shot 3, was repositioned tail in at 1,350 feet. The Buster Jangle B-17 was moved to the 1,500-foot station, where modern propellers were installed. The instrumented aircraft from the 8,000-foot station were moved to a new position adjacent to the 4,000-foot station revetments. At this station, all aircraft, except one F-47, were oriented with their tails toward ground zero. Because of its vertical tail instrumentation, the single F-47 was placed side-in. The B-29 was moved to a nose-in position at a range of 5,000 feet, where an overpressure of 3.5 pounds per square inch was anticipated. At the 8,000-foot station, only one aircraft, a B-17 oriented side-in, was exposed during shot 4. This B-17 had received previous damage while nose-in at 10,500 feet during shot 3. Shot 4 was fired on the morning of 1 May 1952. It was a 20-kiloton device and was detonated at a height of 1,040 feet above the ground. As it was necessary to place aircraft in completely new locations in order to realize overpressures needed to fill in data, it was possible to have only a few cameras in operation during shot 4. For this reason, most of the following motion pictures were taken after the explosion, when it was safe to move in and photograph the damage. All of the aircraft closer than 2,200 feet were demolished by the thermal and blast effects. This F-47 was nose-in at 2,200 feet, where the overpressure was 9.5 pounds per square inch. This F-86 was located nose-in at 2,500 feet overpressure 9.1 pounds per square inch. Most of the damage to the airplane resulted from its nose being lifted into the air, coming down on the tail cone, then on the left wing, and finally on the right gear, which failed. The airplane suffered extensive sandblasting and dents from flying objects and was considered to be damaged beyond economical repair. Many of the aircraft were tied down loosely with field tie-down kits. However, these tie-downs were not effective during high overpressures. The nose-in and side-in F-47s at 2,500 feet were damaged beyond economical repair. The thermal radiation intensity of 65 calories per square centimeter, in conjunction with the 9.1 psi overpressure, resulted in severe burning and shredding of components, some of which were damaged beyond recognition. Oriented left side in at 2,500 feet, the XF-90 had its aft fuselage torn off at the removable joint. Most of the skin panels on the left-hand side of the fuselage were caved in. The nose compartment was shredded, the tail cone blown off, the vertical fin wrecked by thermal shock and sandblasting, and the right-hand stabilizer was broken off, probably by ground contact. The aircraft was rotated about 90 degrees and thrown back 60 feet, resulting in the failure of the landing gear. Oriented tail-in at 3,450 feet, this F-47 was one of several aircraft with supports under the tail to simulate a tricycle gear attitude. The forcing functions at this range were 6.7 psi overpressure and 38 calories per square centimeter. The empennage, the flaps, and the aileron were damaged beyond repair. Replacement of parts and complete repair would require about 1,680 man-hours. In the B-45 oriented nose-in at 3,450 feet, damage was confined primarily to the fuselage. No damage was apparent in the wings or the empennage. A longitudinal buckle extended the length of the aft fuselage on both sides. The main gear doors were broken open, and the bomb bay doors had failed and were hanging loose. Most of the upholstery was charred, and the bombardier's enclosure was sandblasted. The repair estimate was 2,840 man-hours. The aircraft at the 4,000-foot station were subjected to an overpressure of 5.4 psi and a total thermal input of 29 calories per square centimeter. This F-86 parked tail-in suffered less damage than similarly oriented F-47s. The F-47 fighters, which were oriented tail-in behind the revetments individually, sustained less damage than those openly exposed. This F-47 behind the wall revetment had its tail lifted and propeller driven into the ground, probably by movement of the air up over the revetment during the negative phase. However, this airplane would have required only 480 man-hours for repair, as against approximately 2,000 man-hours for an unprotected F-47. The tail-end B-17 at 4,000 feet was almost completely wrecked. The wing structure aft of the rear spar was torn off. The fuselage suffered severe internal injuries throughout, including the frames and stringers and the radio equipment. The aircraft was so badly damaged, it could not be economically repaired. The B-29 nose-in at 5,000 feet was destroyed by fire, which probably started in the webbing and the upholstery of the pilot's compartment. After gaining strength, the fire burned off the nose section, spread through the crew tunnel, and burned off the tail. The 4,500 gallons of high-octane fuel in the wing did not ignite due to the efforts of firefighters who arrived less than an hour after the detonation. Blast damage included crushing of the empennage and the outer wing panels. This side-in B-17 at 8,000 feet was exposed to an overpressure of 1.8 psi and a total thermal radiation of 8 calories per square centimeter. It received significant damage over and above that received on Shot 3. The major new damage was a torsion failure of the fuselage in the area of the wing rear spar and severe deformation of skin and substructure in the vertical tail, fuselage, and bomb doors. the accumulative damage from shots 3 and 4 would require 5,500 man-hours for repair. Although the aircraft fuel tanks contain standard fuels, with some of the tanks full and others partially full for experimental purposes, ignition of the fuels did not occur where the airframe was not completely decimated. There were fires and charring of organic materials in many of the aircraft. Smoldering shoulder harness webbing, headrests, and similar materials were extinguished with carbon dioxide extinguishers by the first re-entry parties, which usually arrived within an hour after the detonation. If these preventative measures had not been taken, fuel fires would certainly have resulted from some of these small fires in organic material, particularly in the case of the B-29 after Shot 4. The results of these tests indicate that fighter-type aircraft which have a structure similar to the F-47 will be damaged by overpressures as low as 4 pounds per square inch. For bomber aircraft, as represented by the B-17 configuration, the damage envelope extends to values less than 1.8 pounds per square inch. The orientation of the aircraft with respect to the blast wave is an important factor contributing to the degree of total damage. In general, the side-in orientation was most critical, tail-in intermediate, and nose-in least critical. Consequently, the term damage envelope can be applied only in a general manner when orientation and other parameters are not defined. Absolute destruction appears to be confined to regions of overpressure in excess of 9 psi for fighter aircraft and 3.5 psi for bombers. The predictions of effects upon modern domestic and foreign aircraft will be based upon extrapolation of the data obtained from and are now the subject of further investigation.